Okay, we continue in a document database. All the data for a particular object is contained within one document, including the subdocument. So as we mentioned before, everything is sitting in one place. Such document is either wholly available for update or it is not. And the database management system can ensure that the update is atomic. We also mentioned about that when we said that we may commit, we commit, otherwise we roll back. Thus, document databases often need not to worry about using transactions to coordinate multiple simultaneous writes, because as we said in document database, everything is in the same place or same document. If, however, a change in a document database requires changes to multiple documents, the update will require the coordination provided by transaction, exactly as what relational database do. We consider some strategies for implementing distributed transactions in two types of systems: the single master system, which we'll focus more on, and the multiple master system. For the first type of systems, the single master system, we have a single master transaction. The system has single distinguished node acting as coordinator. So we have coordinator. All update requests sent to this coordinator. We cannot send to any other server. Any requests should first send to the coordinator. The data may be sharded across multiple secondary nodes. Now, the challenge is to ensure that the transaction is ACID atomic by coordinating access to all the necessary data and either committing or rolling back a transaction as necessary. So in here, the atomicity is the important property that we want to care of. For two-phase commits, we have two phases actually in order to make commit for any update. Simplest approach to ensure atomicity is two-phase commits. This also approach, client interact with the coordinator, as we mentioned previously. The coordinator will ask each of the participants to perform the changes required for a transaction, but not to commit them. Just finish your work, finish your job as participants or server. As each participant completed its update, it tells the coordinator that it is ready to commit. So after they finish, they send message to the coordinator telling that they are ready to commit the transaction. If all participants reach this stage, the master instructs them to commit the transaction. Okay, the participants send back acknowledgement message when they have committed the transaction. So we can see this process in this figure. Okay, we have the coordinator, and this is one participant, and this is the other participants, two servers. Okay, in the first stage, okay, this is the first stage. Okay, fine. You see that the coordinator asks each participants to do the job, responds to the request. After that, each participants will send a message to the coordinator telling the coordinator that yes, we are ready to commit. And in the second stage, the coordinator will send a commit message to each participants, and those participants will commit the updates they made, And finally, after each participant commits its data, it will send acknowledgement message to the coordinator telling that everything was done correctly, and then the transaction will be success. Okay. Now talk about if we have some fail, like if one of the participants cannot commit its part of the transaction, it sends failure message to the coordinator, which then sends rollback message to all the participants, which in turn will then make rollback process to the transaction. The coordinator then tells the client that the transaction failed. As you can see also in the figure, you can see that starting with prepare, they finish their work. Each of them now send, okay, the first one send yes, I'm ready to commit, but the other one send no, I'm not ready to commit. For this, the coordinator will send a rollback message to each transaction, telling the transaction that you need to roll back because they are not ready. After that, after they roll back, the participants will send acknowledgement message here, acknowledgement message to the coordinator telling that everything is completed, and then the coordinator will mark this transaction as failed transaction. Limitation of two-phase commit only work if there are no failure among the coordinator or participants. Otherwise, we will go for rollback even like before, and then the transaction will be failed. Okay, three-phase commit. The problem with two-phase commit then is that some nodes will commit a transaction before all participants know that they should do. Thus, the solution is to communicate the commit rollback decision to all participants before any of them acts on it. Okay, this is done by splitting the second phase of the two-phase commits given three new phases. The first phase is the same as in two-phase commit. The second phase, if the coordinator decides that the transaction can go ahead, it sends pre-commit message. This is the new one to all participants. If it can't, the coordinator send pre-rollback message. The participant responds to that that they have received this message. All participants in the third stage, all participants know whether to commit or roll back the transaction and take the appropriate action. We can look at this. Okay, the first stage. Okay, this is the first stage. We have prepare, and then each participant will send a message to say we are able to commit. Okay, they didn't say yes to commit, they say we are able to commit. Then we go to the second stage. The coordinator will send, this is the new one, will send pre-commit message to each participants and waiting acknowledgement for each of the participants. If the coordinator get acknowledgement from all participants, then it will send do commit to each participants, and after that each participant will send back an acknowledgement to the coordinator telling that everything was done successfully. And this is how three phase commit works. For multiple master transaction, we don't have much to say in that, but we have this comment that a system will have to scale out and accept updates to multiple masters, and the distributed database as a whole will have to deal with any conflict after that. So you know that if we have multiple masters and we send request to each time to different master, then we may get a kind of conflict, and then we need a way to overcome or to deal with this conflict once it is arised. State versus log state, we also mentioned about that or discussed that when we discussed relation database management system, and we said and also in scaling out, I said before that all the servers should have the same state, means the same up-to-date data in all servers. So a request we made to any of these servers will give the same result. The log file, from its name, to store every request in this file. So things are easier if we keep a log of the actions taken at a node. When a node is asked to do something, it logs the request in a cap consistent manner. Log entries cannot be changed once they have been written. When the node recovers from failure, it can replay the log to repair any internal damage and compare its log with logs of other nodes to ensure that its state is consistent with the rest of the system. So if node X is failed and then node Y working, and we have done many requests on node B, okay, while node A is failed, then after node A becomes alive, we refer to its log file and compare it with B's log file and check the missing request and update the database on that. The first algorithm to guarantee consistency across distributed system is called Paxos algorithm. It is very difficult to understand and very difficult to implement. An alternative for this algorithm is the Raft algorithm, which is easy to understand and implement. In conclusion, just summarize this part. We have looked at three methods of preserving consistency in the face of failure. They are two-phase commit, three-phase commit, and Raft algorithm that differ in performance and in the guarantees they make. This is all. Thank you for listening. Goodbye.